Welcome to homework.
This is kind of an interesting problem that, again, there's a lot of math and algebra that I didn't reproduce here just because hopefully you can do that on your own. And so I'll talk more about the mechanics of the problem. So we have a beam that's broken into three segments. And so there's segments here are pin jointed together. So what happens is there needs to be no moment at these positions here. Where they're pinned together. So because the pin can't carry a moment, so support a moment across it. So what we can do is we can draw free body diagrams of each of these. There's a distributed load acting over the entire structure, and if we look at the free body diagrams of each of these balance forces and moments, we can figure out what these reaction forces are, and then also what these internal the reaction forces across the pins are. And because of symmetry, we can see that they're, we have symmetric values. So once we do that, we can then just start taking cuts. So we need to, basically take a cut here and here, and then throughout this region, and then here and here. So in this region, again, we're under a uniform distributed load, so the shear is going to decrease linearly. It's going to start, so I've plotted, because we weren't given values for W or L, I've plotted V over W times L and X over L. L goes from, basically the total length of the beam is 3, so X over L goes from 0 to 3. So we see here that we have a linearly varying distributed shear stress or shear force in this region between these two supports. Then at this support we jump up 10 ninths units, and then we have a linearly decreasing shear in this region, and then we get to and again we have the value here that we don't really need to take a cut there, because that's kind of an internal. This is what the shear stress is. 1/6 is what the shear stress is at that point. And then we jump up again 10 ninths units, and then again we have, in this region here, we have linearly varying shear stress until we get down to the end where we have 7/18 W over L. So that's what our shear stress looks like. So we basically decrease, jump up, decrease, jump back up, decrease. And again, we can see that the symmetry about this line here, I guess basically it's anti-symmetry about this line. Now, for the moments, again, we're going to have quadratic functions. And what we can do is, again, we look at in this range here. So in this range, we start at 0, we come up, and we drop down here until we get to this point. Okay, so again, because the magnitude of the load and the position of the equivalent load are both changing linearly with X, we get a quadratic function. And again, we can just, if we just do the shear, the force and moment balances on an arbitrary section, we can figure out exactly what this function is. And then in this region, we can come through here, and we can basically see that we have it changes direction, and we rise up until we get a little above 0 at the middle, and then we come back down. And then over here we have the mirror image of this. So again, we have symmetry about the center, where we have anti-symmetry here. And again, I plotted m over WL squared and x over L. So we can see that, again, indeed, we have 0 moment at these points here. That's these points here. We also have 0 moments at a couple other interior points. Those would be just to the right, or to the left and to the right of these supports. And then obviously at the ends we have no applied moment, so the moments are 0 there.